All right, hope that works. Yeah, so I was asked to talk a bit about my background and my path and how I got here, and that's what I'm going to start with. So my name is Valentin. I grew up in the north of Germany, and then I moved to Göttingen for my bachelor's. That was in pure math, and so there I didn't do much data science or computer science in general yet, but I already got interested in probability theory and statistics, and my thesis worked on optimal transport, which produces these nice pictures and is also related to those topics. Then I wanted to continue this path of statistics, stochastics, and so on. And in Munich, they had just started a new master's program called Mathematics and Data Science. So it was still math, but with a focus on data science, data analysis, and machine learning. And yeah, I thought this would fit me quite well. And while I was there, I applied for the summer at EPFL internship program. For those of you who don't know, this is a program by the IC school where every summer they invite around 50 students from different countries, but I think also from Switzerland, to come to EPFL and work in one of the computer science labs on some research topic. In my case, I worked with Bob West from the data science lab, and we had a collaboration with Clicks. That's a company that develops a search engine and a browser. And originally, we wanted to do something more traditional from the data science space, so analyzing some of their customer data to get some insight. But they had a quite strong focus on privacy. And so we thought what might be actually even more interesting would be to think about how to do machine learning data analysis with privacy constraints. And at that point, neither of us had done anything with privacy yet. So it was new for both Bob and for me. And yeah, nevertheless, we did a quite interesting project there, which then also led to a publication. Unfortunately, shortly after I finished my internship, and even before the publication got published, Clicks went out of business. But I hope it didn't have anything to do with our collaboration. And at least I got a lot out of this internship. Because then I moved back to Munich to finish my master's, but I liked working in the data science lab and with Bob and on such topics so much that I decided to apply for a PhD, and then came back to Switzerland, and now I'm working on my PhD with Bob on privacy topics. And if you have the chance to do such a research internship, to already work with a potential PhD supervisor before starting a PhD, I would strongly recommend you to do this. It's very hard to just from one or two interviews know whether you would really work well with a potential supervisor. Whether your working styles match, also whether your interests match. And for me, this was a great opportunity. Before that, I didn't even know whether I wanted to do a PhD. But yeah, the summer was just great experience, and I thought I want more of that. So people are boring, ideas are interesting, and this is why now we move on to one of the most influential ideas in privacy in this century. which is differential privacy. And kind of throughout the first half of my PhD, I mostly worked on this topic. And this presentation is going to give you a bit of background, a bit of what people do research on, but it's also to a large part a tutorial for you to get started with differential privacy. Why do we need privacy enhancing technologies in the first place? Give you a moment to read the XKCD. The idea here is that even if you don't publish data verbatim, so you directly release the database out into the open, but you only release some data that is derived from the original raw data, you might still reveal sensitive information that's contained in the original data set. In this example, there's someone in possession of a sensitive data set with private messages, and they train a next word prediction model on that data. And you might think, okay, this is a model that has learned some general information about the distribution of text. But there are a lot of works that show that this is not necessarily the case, and that such models still contain and learn information about individual records in the database. That's not only a problem with machine learning models, but more generally, whenever you release the result of some function computation on a database, can also be more simple statistics that you reveal something about individual records in the database. The idea behind differential privacy is to prevent such leakage of sensitive information about individuals that contribute data to the database. Nowadays, it's been adopted by a lot of the big industry players, so Apple, Google, Microsoft, and very prominently also the US Census Bureau. So they used differential privacy to protect the privacy of individuals who contributed to the 2020 census, which was a big step, because before they only used heuristical privatization techniques such as anonymization and other things that don't give formal guarantees. And this is one of the strengths of differential privacy, that it gives a mathematically strong privacy guarantee. And secondly, that it's also achievable, meaning that it's general enough so that it can be applied to a lot of settings of practical interest. The one downside of differential privacy is that you typically need a sufficiently large database, because it is based on adding noise, as we'll see in a bit. And so if your data set is too small, then you get a bad signal-to-noise ratio and you lose a lot of utility. The setting that we are operating in is as follows. So we have a database that contains potentially privacy-sensitive information. And then we have this kind of safe space within which we can query the database. So you can think of some research institution having collected survey data of individuals, and the researchers can do science with this data. And so as long as it stays in the lab, this is not problematic, because kind of the study participants trust the researchers. Or a different setting would be you have a company that has user data on their servers, and so the company can analyze this data. And this in itself is not a privacy threat yet. However, now the party that possesses the data decides to release some information about this data. So in the example of researchers, this could be a study that, for example, analyzes the efficacy of a certain drug to treat some disease, or in the case of companies, this could be a company that uses their user data to train a machine learning model and then wants to deploy this machine learning model in the wild. So as in the XKCD cartoon, this could, for example, be Google, who has collected data from Android users, trains a next word prediction model or an autocorrect model, and then ships this with Android to end users. And now this model is out in the wild and everyone can see it. And to prevent such a thing as in this cartoon, that people can use their access to the model to extract parts of the sensitive data that it was trained on. The idea of differential privacy is to add noise to everything that leaves this safe space here. So in the case of the model, you could, for example, add noise to the parameters of the model, and you do this in such a way that you can guarantee that all information, or almost all information, about individual records in the database is hidden. What do I mean with this more precisely? This red and this blue database are exactly the same, except that in the blue database we are missing one record. Now, we are interested in releasing the result of some function computation f that is computed on this database. So this could be some statistics, this could be a machine learning model trained on this database. And we want to release this to the public. Now, if this is a deterministic function and the databases differ even only slightly, then in most cases of practical interest, the result of this function computation will also differ slightly based on whether any particular record, such as this one, was contained in the database or not. And this is why we'll get these two slightly different outputs on the two databases. And an adversary that is interested in information about this record will be able to determine whether this record was contained in the database or not, based on the function output. Talking here about learning about whether a particular record was part of the database or not. But this is more or less equivalent to learning certain entries of this record. And so you can always think of these two things as equivalent, because in a practical setting, probably if this is medical data, this would be a record corresponding to one person, and then one of these entries might be, does this person have a particular disease, and adversary might be interested in the value of this attribute. Okay, back to this problem here, that we can decide based on the output of the function whether the record was contained in the database or not. And to solve this problem, the idea of differential privacy is to add noise to this function computation. And what this means is that whenever we release a function value, we first sample noise from some distribution and add this noise to the function output. What this means is that then we'll end up in the setting on the right, where our output is now not deterministic anymore, but instead it's a sample from a probability distribution. The distribution that we sample from still differs based on whether any record is part of the database or not. And so there's still some information about record membership contained in the output of this noisy function computation. But the idea of differential privacy is now to bound how much information is contained about record membership. And the way differential privacy does this is that it bounds the ratio of the probability densities at any point in the support of the probability distribution. So that these two curves may never deviate too much from each other. And formally, it can be written as this. And here we bound the ratio of the probability distributions, or the logarithm of that ratio, by a value epsilon. And if this ratio is bounded everywhere by this value epsilon, then we say that an algorithm fulfills epsilon differential privacy. In practice, we need to choose some value for epsilon. If you remember the formula from the last slide, the smaller epsilon is, the more privacy we have, because the closer these two output distributions are to each other. How do we now choose epsilon or interpret the value of epsilon? We can think of an adversary that has no information about whether any particular record was part of the database or not. So their prior suspicion about database membership is 50%. Now they receive the output of an algorithm that fulfills epsilon differential privacy. And then we can mathematically show that their posterior suspicion, so the belief about database membership after they've seen this output, can be bounded as follows. So for epsilon equal to 0.5, it's bounded by 63%. For epsilon equal to 1, it's bounded by 74%, and so on. And in practice, usually you would choose epsilon equal to 1 or smaller, because, yeah, you could say in adversary that can say with at most 74% confidence that record is part of the database or not is not a very strong adversary, and they haven't learned a lot, or they cannot be very confident in their new belief. There's a slight extension of epsilon differential privacy, which is called epsilon delta differential privacy. This is quite often used in practice, and it's more of a technicality, because here we additionally have this additive delta term. And the way you can interpret this is that with a small probability delta, where the probability is with respect to this, the distribution of this noise, the epsilon differential privacy guarantee will not hold. This is not entirely correct, but in practice you can think about it like this. But just keep in mind that it's incorrect. Okay, how do we build differentially private algorithms, or in the DP lingo it's usually called mechanisms for historical reasons. The most basic one is the Laplace mechanism. And so for this, again, we have a function f whose result we want to release. And we need the L1 sensitivity of this function to be bounded. The L1 sensitivity is just the maximal amount by which the function value can differ if we add or remove one value from the database. So we look at neighboring databases, x and x prime, where neighboring just means differing in at most one record. And then we want to bound the L1 norm of the difference of the function values on these two databases. Now, if we have such a bound on the sensitivity of the function, and for a lot of functions of practical interest we have such a bound, then we can simply compute our function f. And at a sample from the Laplace distribution with parameter sensitivity over epsilon. This parameter is directly the standard deviation of the noise distribution, and so here we see the larger the sensitivity is, the larger the standard deviation of the noise is, so the more noise we need to add, which makes sense because the function output can potentially reveal more about database membership, and the smaller epsilon is, the larger the standard deviation is as well. So the more privacy we want to get, the more noise we need to add. As a running example for building something useful with this, we will look at a machine learning model that we want to fulfill differential privacy. When training a model, or like the life cycle of a model usually consists of first training. And then once you've trained the model and you want people to use it to make predictions, one thing you can do is you can publish the model, or you can provide an API for people to query the model which is hosted on your service, and they get predictions back. Now, two ways to achieve differential privacy would be to first train the model, then add noise to the parameters of the model, or to add noise to the predictions of the model and never release the model parameters. Both of these things work, but typically neither of those is used in practice. The problem with computing the model parameters and then adding noise is that it's very hard to compute the sensitivity of the function that trains a neural network. And so this only works for very simple models. And the problem with adding noise to the predictions is that you need to add noise to every single prediction. And that with every single prediction, the adversary learns more about your model. And so this only works if you really allow for relatively few predictions. So what people do instead is they add noise during the training of the model. This is somewhat equivalent to to first training the model and then adding noise to the parameters, but it's more practical since you don't need to compute the sensitivity of the final model. So how do we make model training differentially private in practice? So the standard way to train a neural network without differential privacy is that you do multiple steps of mini-batch gradient descent. So first you sample a random mini-batch from the training data, then you compute the gradient of this mini-batch, and then you perform a step in the opposite direction of the gradient. You perform this many times, and then you perform this whole thing again many times to do hyperparameter optimization. To make this differentially private, you essentially only need to modify one step here. That is the computation of the mini-batch gradient. And that's very nice about training via mini-batch gradient descent, that you only need to change one step, and changing this step is very simple because the basic idea is to compute the gradient and then add noise to this gradient and then do the gradient step. For doing this and for knowing how much noise we need to add, we need to know the sensitivity of the computation of the gradient. And the small problem with neural networks is that, in theory, changing only one record in the data set can change the value of the gradient in arbitrary ways. So if you are very unlucky with the current weights of your model and with the record that you choose, then the gradient can become arbitrarily small or arbitrarily large. So how do we get around this? In a relatively crude way. So we just force the gradient to have a small norm. The way we do this is we define some maximal norm that the gradient may have. In our case, here we just say it's 1. And then if the norm of the gradient is below this norm, then we just take it as it is. And otherwise, we clip it, meaning we just shorten the gradient vector by its norm. That way, we have bounded the sensitivity, and now we can, for example, add noise via the Laplace mechanism. A different thing that you can do whenever you cannot bound the sensitivity of a function that you're interested in is to perform what's called sample and aggregate. What this does is it first splits your database X into k disjoint databases. Then you compute the function value on each of these disjoint subsets of the database. And then you aggregate these function values with a robust estimator, so for example, with the median. And then the only thing that you need to do is to bound the sensitivity of this aggregation function in the end. And for example, for the median, you can bound this quite easily. And the nice thing about this is that it's completely independent of the function f that you're interested in. Coming back to neural networks. One small technical detail. So far, I've presented to you the Laplace mechanism, which adds Laplace noise. This is a very simple mechanism, and it usually works well for low-dimensional settings, where the amount of noise that needs to be added is relatively small. However, for high-dimensional settings, people usually use the Gauss mechanism, which, as the name suggests, adds Gauss noise. And here, the standard deviation of the noise that needs to be added scales only with the square root of the dimension of the function output. And so for high-dimensional settings, such as training of neural networks, this is typically what people use. So now we've made each gradient descent step differentially private. Now we also want to make the hyperparameter optimization differentially private. And this first might seem a bit tricky because what you do with hyperparameter optimization on a high level is you train several models and then you compute, for example, the validation loss of these models, and then you pick the one with the smallest validation loss. But this operation is kind of picking one candidate out of a set of candidates, and it's very different from releasing like a continuous value to which you can just add noise. Fortunately, for such settings, there also exist differentially private mechanisms. And the most basic one is the so-called exponential mechanism. So first we define a utility function. In the case of hyperparameter optimization, this function could take in a database and a model, and would output the validation loss of that model on the database. Now, what the exponential mechanism does is, again, it doesn't produce a deterministic output, but it produces a sample from a probability distribution. And this probability distribution is such that you have a higher chance of outputting values that have a higher utility function. So it kind of, like if you wouldn't use any differential privacy, you would always output the max. And this can be seen as a kind of softmax operation where you also give a bit of chance to lower utility outputs to be returned. Finally, I've said that we have made the gradient descent steps differentially private, but we need to do several gradient descent steps. And there's a small problem with this because every time you release some information about the database, you also release some information about individual records. And so if you would just naively take some differentially private mechanism and then create outputs from this mechanism a lot of times, then an adversary could just take the mean of these outputs and because of the law of large numbers, the noise would just cancel out and they would get exactly the noise of the original, the value of the original function without any noise. And therefore, we would have lost the advantage of differential privacy. And so this means that whenever you're in such a setting where you produce multiple outputs with differential privacy, you need to account for this fact and add more noise in, to every single output. There are theorems that tell you how much noise you need to add. Essentially, if you have few iterations, then and you produce every single output with epsilon prime differential privacy, then the overall privacy guarantee that you get is k times epsilon prime. So you need to multiply the amount of noise that you need to add by k. If you have a lot of iterations, then you can use some nice mathematical tricks so that you only need to add square root of k times as much noise. And there has been quite a lot of work on this to get better so-called composition bounds, and this is also a field that I did some work on. By now it's mostly solved, I would say, so there are still a few improvements that you could make, but it's like harder and harder to make research progress on this problem because it's such an important problem and people have spent a lot of effort on it. Okay, so we've made new network training differentially private now. And now we can look at how to do a couple of optimizations. And so one optimization is to look at this first step where we randomly sample a mini batch from the database. And intuitively, this should allow you to get away with adding a bit less noise than you would add naively, for two reasons. First, because you sample a mini batch, you don't compute the gradient on every single record. So for most records, the mini batch gradient will contain zero information about these records because they're not even used to compute this output in the first place. The second reason is that we perform random sampling. So there is some randomness already in this standard way of training neural networks. And this means that we need a little bit less randomness from the noise that we need to add later on. And both of these intuitions actually hold true. So there are so-called amplification theorems that tell you that if you subsample your data and only compute your function on a random subset, then if you do the subsampling with probability p, then your delta decreases by exactly this factor p, and your epsilon also decreases in a slightly more complicated way, but essentially the smaller your p is, the more epsilon decreases as well. In the remainder of the time, I'll just go through a couple more applications and briefly tell you how differential privacy is achieved there. So one very simple application is the release of frequency histograms. So histograms are kind of nice in the sense that every record increases one of the counts in this histogram by exactly one. And so this means that the histogram function has sensitivity 1, and we can simply make the histogram differentially private by adding Laplace noise. Another application is k-means clustering. There are different ways to make this differentially private. So one is to use this sample and aggregate method that we've seen earlier. Another one is to use an iterative algorithm for computing the clustering, such as Oy's algorithm, and add noise in every single step of this algorithm, so a bit similar to what we do for gradient descent. And finally, we can also use Lloyd's mechanism, but not add noise directly, but instead in every iteration where we choose the new cluster centers, we don't choose the best ones, but we sample approximately the best ones via the exponential mechanism. We can also make principal component analysis differentially private. Here we look at the application where you want to publish the eigenvectors. One way to do so is to simply compute the PCA non-privately and add noise to the final matrix. Another one is to use the power method, which is also an iterative method, and add noise in every iteration. And another one is to compute the PCA non-privately and use the exponential mechanism to sample eigenvectors in the end. And you might see a pattern here, namely that a lot of these mechanisms work with these very simple building blocks that we've already seen. And this is a general pattern. So for a lot of applications of interest, you only need to know like 3, maybe 1 or 2 others that I haven't shown here, basic building blocks, and you can already make your application differentially private. And it's relatively rare that you need more fancy methods or more fancy math to achieve differential privacy. Another application are graphs. Graphs are a bit tricky because there it's not so clear first how to compute sensitivity. So you first need to define like what piece of information we even protect. And so one thing you can protect is the presence or absence of nodes, and another thing is the presence or absence of edges. But even then, it's like a graphs with a lot of structure, which means it's hard to add noise without destroying a lot of utility. But there's still a couple of things that you can do. For example, you can release the degree distribution or the number of triangles in a graph with differential privacy with relatively little noise. And finally, so far we've discussed settings where you know the function that you want to compute on the database and whose result you want to release beforehand. But there are also many settings where you might want to release data, for example, to researchers who can then come up with their own things to compute on the data and their own applications. And for such settings, you can think of releasing datasets with differential privacy. What doesn't work easily is to just take your dataset and add noise to it and release that, because since you want to protect every single record, you need to add a lot of noise to every single record, and so you'll end up with a very noisy dataset. But what people do instead is they release synthetic datasets that are based on the original dataset. One theoretical way how you could do this is to create a synthetic dataset via the exponential mechanism. and can be shown that this is optimal in some ways. However, it's just a theoretical thing because for the explanation mechanism, if you remember, you need to sample from some probability distribution. And here you'd need to sample from the kind of the entire set of potential records that you could release, which is a very high dimensional space, and you need to explicitly compute this probability distribution. So in practice, this usually doesn't work. What people do instead is, for example, that they compute a Bayesian network where they compute the correlations or associations between different attributes in the data, and then also the marginal distributions of the attributes, and then generate synthetic records from that Bayesian network. And if you want to go the full-on ML route, you can also train generative models such as autoencoders or GANs with differential privacy, as we've seen before. Or you can train them without differential privacy and then take records from the original data set, feed them as seeds into the model, and then add some noise and some latent space there, and therefore create records that are similar to individual records in the data set, but not exactly the same. To conclude, differential privacy is a widely used notion of privacy. One of the main reasons is that it can be applied in a lot of settings, and it's relatively easy in a lot of cases to achieve differential privacy. There are a couple of important building blocks that were already discovered pretty early on in the history of differential privacy, and which can be used to build most DPE applications. The one downside of differential privacy is that because it's based on adding noise, you need a sufficient amount of data so that your signal-to-noise ratio is large enough. If you want to get started with differentially private machine learning, there are two pretty mature libraries, one for TensorFlow and one for PyTorch. So for TensorFlow, it's part of the main distribution. For PyTorch, it's called Opicus, and they use state-of-the-art methods for DP, and it's pretty straightforward to train a machine learning model with differential privacy. There are also a couple of other libraries for doing more basic statistical tasks with differential privacy, but they are not as well maintained and supported as those machine learning libraries. And often these algorithms are also not super fancy, so there basically you can also implement things from scratch if you want. Yeah, that concludes my presentation. And if you have any questions, now is the right time for that. Thank you.